Now that's all fine if we're looking at a CW signal, but of course most of the time we're going to be looking at modulated carriers. And as I'm about to show you, the standard markers are not that useful in that situation. Here I'm generating a spread spectrum signal at 2 GHz. I'll just tune in, center frequency 2 GHz, and let's enter a span of say 10 MHz. Now this signal here is in fact a W-CDMA signal, as I say, that's at 2 GHz. Now if I put a marker on there, there's the marker, and you can see it's at 2 GHz, and the level is around minus 25 or something dBm. Now that's fine, it is in fact truly measuring the power at that spot frequency, but in the case of this modulated carrier, you can see that the power is in fact spread across a whole range of frequencies, the channel bandwidth of a W-CDMA transmitter. So we're not actually measuring the total power of this transmitter. Fortunately, these analyzers have a very useful feature built in for doing that. If I press the measure key and then channel power, and I'll set the integration bandwidth to say 4 MHz, and the span is still set at 10 MHz, what's now happening is that the analyzer is integrating under the curve, in other words, counting the squares, adding up the total amount of power within these green channel power markers. And you can see in fact that whereas the single marker 1 is measuring about minus 25 dBm, you can see here that the actual channel power is much greater than that. It's about minus 11 dBm. So you can see it says channel power minus 11 dBm per 4 MHz, so in the 4 MHz bandwidth, but it also gives us power spectral density of minus 77 dBm normalized to a 1 Hz bandwidth. Now in this instance with the W-CDMA signal, I know that the channel bandwidth is about 4 MHz, but let's say there's a modulation on a carrier from a satellite or a Wi-Fi signal or Bluetooth that I don't know how wide the modulation bandwidth is. If I press return and press occupied bandwidth, now this is very, very similar to channel bandwidth. In fact, it looks almost the same, except you'll see now that the green markers are not fixed at a 4 MHz channel separation. They're actually moving and adjusting in real time. And in fact, what's happening here is the analyzer is automatically measuring within what bandwidth 99% of the power on the display is contained. That's varying slightly because of the noise on the signal, but you can see here that the occupied bandwidth is about 4.1, maybe 4.2 MHz. It's also measuring what's called the bandwidth centroid. So let's say this signal is nominally transmitting at 2 GHz, which we know it is, but let's say the modulation is not symmetrical about the center frequency. This bandwidth centroid will tell you what the actual center frequency is. In other words, the center point between the two green markers, which may or may not be the same as the nominal center frequency of the transmitter. A very common problem these days at transmitter sites is interference from one transmitter into perhaps the receiver of another radio that's co-located at the same site. So how do we go about measuring the power generated by this transmitter in the adjacent channels, which one would think were going to be probably the most likely spot where this transmitter might be leaking into and causing interference? If I press the return soft key, you can see there's another useful measurement here called adjacent channel power, ACP. Now here, of course, again, we're going to need to set up the channel bandwidth. So if I say that the main channel is 4 MHz wide, and maybe the adjacent channel I'll also set to 4 MHz wide, but I don't have to. And the adjacent channel spacing I'll set to say 10 MHz. And we'll just widen the span a bit. If I press span and let's go out to say 30 MHz. You'll see now that as well as measuring the channel power in our main channel, the intended frequency of transmission, we're also measuring the adjacent channel power in these two adjacent channels. So as well as measuring the power in the main channel here, it says main channel power about minus 11 dBm, we're also in the table below measuring the adjacent channel power for both the lower and upper channels, adjacent channels, and you can see that the channel power, the absolute value in dBm for this adjacent channel here is minus 56 dBm. And it also gives you a relative measurement, in other words, comparing the level here to the level of the center channel, and that's minus 45 dB. And then we've got the same again for the upper channel. And in fact, we don't have to just do it with 2 adjacent channels. As you can see here, we can have up to 6 adjacent channels on either side of the main channel. And in real time, the analyzer will tell us the absolute values and the relative values relative to the main channel power. If you'd like further information on these products, including demonstration guides, operating manuals, or application notes, please visit the website shown below.